kind of where we're headed. So let's just go ahead and start. So these were all in the video. So just make sure that you are completely familiar with these. And I think I even gave you English versions. Like, for instance, for number 1, I wouldn't have just said a raised to the x times a raised to the y is equal to a raised to the x plus y. Let's move on. More than likely, the way that I worded it, and I don't remember because it's been so long, is I probably would have said, when you're multiplying like bases, keep the base and add the powers. Does that ring a bell? Yeah, because that to me just makes more sense. So multiplying like bases, keep the base, add the power. Same with number 2. Number 3, I probably would have said raise a power to a power, et cetera, et cetera, et cetera. This right here is basically something that I found on Pinterest. And it's the nice thing about this is that it's the exact same list of rules, but they give you some examples of what it looks like, and they give you even why it works. Okay, so that's why I like this graphic. I'm not going to go through it, but if you're really struggling with remembering a rule, then what you might want to do is you might want to work through, okay, why does this work? Okay, and then that will help you to remember a rule. All right, so we've got a new parent. So now let's see, goodness, we're really racking up on parents, right? We had our 6 parents back in chapter 2. And then in chapter 5 was our first set of new parents, and that was the reciprocal and the reciprocal square. So that's 8 parents now. And now I've got parent number 9. This is going to be the exponential parent. When I get into logarithms, I'll have some logarithm parents. So we have the exponential parent. The exponential parent, y equals a to the x, blah, blah, blah. This parent's a little different. You see the stars there? Because he can have an infinite number of different a values. So like my parent might look like this guy right here, y equals 2 raised to the x. Or maybe my parent will look like y equals 4 to the x. Or y equals 1/3 to the x. Or y equals 10 to the, you get the idea. So these are all the same exponential parents, okay? And so I'll show you how to know the difference between them, but just understand that my parent equation can look a little different. You know, for the squaring parent, it's always y equals x squared, y equals x squared, y equals, that's his parent, and it doesn't change. But this guy changes. All right, so it looks like the embedded question was where we graphed, and I walked you through graphing, but I'm guessing you had to go find the domain, the range, the y-intercept, and the horizontal asymptote for the embedded question. Okay, so domain then, when you're looking at the graph, what did you find for the domain? Say it again. Yeah, negative infinity to positive infinity. All right, somebody else. Hey, there's 4 questions and there's 4 of you. Mary Alice had to take a test this morning at her high school, so, and that's why she's not here. So one of the other 3 of you, what's the range? Good, 0 to infinity. And I'm not including the 0 because that's a horizontal asymptote. I'm getting closer and closer and closer to it, but I'm not actually getting there. All right, one of the other 2 of you, y-intercept. All right, the coordinate, 0, 1. This is what I would consider my special point. Okay, and then the other special point that I'll go ahead and mention it right now. The other special point is going to be when my x value is 1. When my x value is 1, my y value is going to be whatever the base is. Okay, so my second special point, we've got 1. In this case, my base is 2, so it's the coordinate 1, 2. If this were 10 to the x, my second coordinate would be 1, 10. If this were 4 to the x, 1, 4. Okay, etc. And I'll dig into that just a little bit more. And then finally, whoever didn't, was that you, Devin, that hasn't answered yet? What's the horizontal asymptote? Y equals 0. Okay. All right, so so this is just an example. All right, so let's do this. Let's graph this one without a calculator, knowing what we know about our parents and descriptions and translations and all that other kind of stuff. Yeah. Okay. Now, I gave you a hint here and I said, let's use some negative powers and translations. Does this look like one of my parents? Well, my only parent. Yeah, it does. But what is it about this one that we don't like? It's not like the example that was in the video. I've got a fraction, okay? Now, you might want your list of rules out from the very beginning of this section, because I'm gonna refer back to these rules. So I'd like for you to look at rule number 7. Rule number 7. What does rule number 7 use? Negative exponents, yeah, negative powers. Negative powers make you move. So if you have a negative power, and it's on top, you can move that whole entire, the base and the power to the bottom. When you move it, the power becomes positive. All right, so negative powers just make you move. They make you move to the top or make you move to the bottom. So, do you like the 4 on the bottom? Because, I mean, that's a fraction, right? Wouldn't it be nice if we could move the 4 to the top and the 1 to the bottom? I can do that by rule number 7. I'm allowed to move tops and bottoms as long as I negate or change the sign of my power. So then how could I rewrite this guy to make it not a fraction? No, so the negative, I'm not changing the sign of the base, I'm only changing the sign of the power. 4 over 1, which I don't need, to the negative x. Does that make sense, Devin? Okay, and actually, Devin, you made a mistake that is really, really, really common. So I'm glad you made it so that we could talk about it. So yeah, you're not changing the sign of the base, you're changing the sign of the power when you move things. Okay, so now when we think about translations, okay, this is one of our parents. What do negatives do to our parents? They reflect. Now, where would the negative need to be to reflect over the x-axis? Out in front. This guy isn't out on front. Okay, now we haven't really run into this a whole lot this semester. What happens with that negative is on the inside. Remember back in chapter 2 having the discussion about insides and outsides. What happens when the negative is on the inside? Reflects across the y-axis. Okay, so this guy, it's a normal parent, except that he's going to reflect over the y-axis. All right. So let's go and we'll work our graph. Now, the things that I would expect to see on a paper graph, I would expect to see your horizontal asymptote, and I would expect to see 2 special points. Okay, so, and obviously the curve. Okay, but we'll get to that after we get the other 2. So when I take my horizontal asymptote, okay, am I shifting it up, down, right, left? Am I doing any shifts? Is that in my description? No, it's not. Okay, but I am reflecting it over the y-axis, right? So now it looks like this. Has that changed? No. Okay, so my horizontal asymptote then is going to be still on the y-axis. That's really not visible at all. So we'll do that and make it visible. Okay. How about my special point? What's one of the special points? Okay, let's do that one in a minute. What's the other special point? Look at the last example. 0, 1. Okay. Now, so let's take 0, 1, which we'll say is right here. Okay. Reflect it over the y-axis. What does it look like now? It looks like 0, 1. Reflected over the y-axis, right? It doesn't look any different. Okay, so let's put here 0, 1. Okay, now let's go to the other special point. What was it you said the other special point was? So when x is equal to 1, what normally would the y value be on this guy? The base, which is 4. Still gave that away. All right, now Sierra's not the only one in the room. Okay, all right, so we've got 1, 4. Oh, but I need to reflect that over the y-axis, okay? So if I've got a coordinate to the right 1 and up 4, and I reflect that over the y-axis, where is that gonna land? Sierra's not allowed to answer for the next 3 questions.
-1, 4.
Yeah, over here, right? -1, 4. Okay, so let's put that in there then. So here's -1, here's 4. All right, now before I go and draw my curves, because that's all the special stuff, the horizontal asymptote and the 2 special points, that's what you're gonna start all these graphs with. Let's go back to that parent graph. I guess this is where the parent graph is. And let's look at what the curve looks like, okay? Notice that the right-hand side of the graph, okay, when I talk about the right-hand side of the graph, I'm talking about, stop, come on, behave. Try it one more time. The right-hand side of the graph, I'm talking about this side of the graph, okay? Now, how would you describe just the right-hand side of the graph? What does it kind of look like? Kind of looks like a parabola, doesn't it? Okay. Now, go over to the other side of the graph. Let's go over to the left-hand side of the graph. How would you describe that side of the graph? Yeah, exactly. It's getting closer and closer and closer to my horizontal asymptote. Okay, so that's left and right. So now what we want to do, though, is on our graph, we need to reflect over the y-axis. So we want to trade the 2 sides. Okay, so let's come back then to our picture. And we can see that our special points are helping us out with that. So now, instead of the right side being the half parabola, now it's on the left side that's the half parabola. And now on the right side, that's the one that's going to look like it's getting closer and closer and closer to my horizontal asymptote. If you graph this on the calculator, it actually kind of looks like it runs into the x-axis simply because the pixels are a little too big. Okay, so, but it doesn't. It doesn't. All right, next. I got to tell you, these are some of my favorite questions in this whole entire chapter. Okay, so we're solving without a calculator. And the tip is, and by the way, we're going to use this tip through several different sections. The tip is get your bases alike. Now, let me give you a hint here. When you're getting bases alike, 95% of the time, you're gonna make your bases smaller, not larger. Okay, when you're getting bases alike, you're gonna make your bases smaller, not larger. There's one example where we're gonna make our bases larger, and I'll show you what that is. Okay, but the majority of the time, you're gonna make bases smaller. Okay, so right now, let's take a look at number 2.
Wasn't that on the video?
I don't know, was it? Was it? All right, then you explain it to me.
So you turn 125 into 5 to the third.
Why?
So that the bases are alike.
And what's the value of 125 compared to the value of 5 cubed? They're the same, which is why I'm allowed to substitute, right? Okay, and then what did I do?
And then you simplify, which means you multiply 3 and x. So you get 5 raised to 3x.
Okay, so I was using a rule for that, right? That was raising a power to a power rule. What was that, rule number 3? Or was it rule number 4? 3, okay, so raising a power to a power, you multiply your powers. Okay, so now I have 5 to the 3x equals 5 to the first, right? And then what? Why am I allowed to do that? Hey, are the two sides equal to each other? How do you know that?
The bases are the same.
How else do you know that? This is one of those duh questions.
It says equal.
There's an equal sign between them. They're equal, okay? Because I'm not gonna lie to you about that. If I tell you two sides are equal, they're really equal, okay? So my sides are equal. Think about it like this. Let me give you just a little, I'll erase this. If I have something like x over 3 equals 7 over 3, are those two sides equal to each other? Yes, they are, because there's an equal sign between them, okay? Now, look at the pieces that are already, I could cross multiply, right? And I could solve. But there's an easier way. Look at the pieces that are equal to each other. Are there pieces that are equal to each other? Yeah, the bottoms are equal to each other. Well, guys, logically, if the bottoms are already equal, what can we say that the tops have to be? They have to be equal, logically. And if you cross multiply, you're gonna find that your x value that's missing is a 7, okay? So logically, when I've already got pieces that are equal to each other, the rest of it has to be equal. And so what we have here is, in this example, when you've got 5 to the 3x is equal to 5 to the first, you've already got bases are alike. So logically, if the bases are already alike, that means the powers have to be alike. Okay, logically. So that's why we set up a little mini equation, 3x equals 1 divided by 3. All right, now, so then how many of these did I do on a video? Just that one? Okay, good. Let's go to number 4. I'll come back up and do number 3 in a minute. Let's go to number 4. Okay, so using that last one as an example then, and can I just say thank you for watching my videos? I appreciate that. I appreciate it, okay? It makes a world of difference. What can I do with this if I'm gonna follow after the same concept? Again, the tip is get the bases alike first. Very good. So we've got 5 to the 2x plus 1. I'm just copying that side. Is equal to 5 squared. All right. So bases are alike. Logically, my powers have to be alike. So let's go ahead and set up a mini equation. 2x plus 1 is equal to 2. Power equals power. Okay, you guys know how to solve this. What should you do? Move the 1, so that's going to be 2x equals 1, and then, so x equals 1/2. Now, what would be a good way, do you think, to check your work if you were just not you weren't sure of yourself? Plug it in. Yeah, look at it. We got x to the 1/2, x equals 1/2. So what's 2 times 1/2? What's half of 2? What's 1 plus 1? Is 5 squared equal to 5 squared? Yeah. So you can plug it in then to check it. All right, let's take a look at number 3 because this looks ugly. All right, here's what to do when you run into fractions. So you might want to write this little tip in the margin. Don't look at this as a 2/3 and a 9/4. I want you to see this as this group of numbers, and this group of numbers is I've got some 2s, I've got some 3s, I've got some 9s, I've got some 4s. Okay, 2s, 3s, 9s, and 4s. So don't look at it as a whole fraction, 2/3 and 9/4. So 2s, 3s, 9s, and 4s. Now, what was it I said about changing bases? The majority of the time, we're going to make our bases smaller. All right, according to that, if the majority of the time we're going to make our bases smaller, do you want to work with the 2s and the 3s, or do you want to work with the 9s and the 4s? The 9s and the 4s, because we can make them smaller, okay? But the 2s and 3s, we would have a hard time substituting something in for 2 to make it a smaller base, right? But we can substitute something in for 9 to make it a smaller base. Okay, so then let's leave the left side alone and let's only work on the right side for right now. Okay, so what is a number that we can turn 9 into to make it into a smaller base? 3 to the second power. Remember, this has to be a pure substitution. So I can't turn 9 into a 3, but I can turn 9 into a 3 squared because they're the same thing. Pure substitution. Okay. What about 4? What can I turn a 4 into? 2 squared. All right. Would you please look at your list of rules? And I'm going for, I believe it's rule number 5. Rule number 5. Does rule number 5, either side of rule number 5, does it look at all like what I just wrote down? It does. So how can I take rule number 5, the way it's written on one side, and turn it into the other side? Because really, when you look at the other side, this is what the other side of rule 5 looks like, right? Okay, so how can I take this guy and rewrite it so it looks like the other side of rule 5? 3 over 2, parentheses, to the second power. All right, now I have a question. What was my goal here? I mean, my goal was to find x, but what was how was I supposed to do that?
Like bases.
Getting like bases. Are my bases alike? No. No, but they are close, aren't they? They're closer than they were a few minutes ago. What does rule number 7 say? Oh, because negative powers make you move. So what you're telling me, Abigail, is you don't like where 3 is and you don't like where 2 is, so you'd like to move them? I love that. Okay, so if I'm going to move the 3 to the bottom and if I'm going to move the 2 to the top, what does my power have to become? So those negative powers let you move top to bottom, bottom to top. Hey, are my bases alike? Finally. Okay, logically, if my bases are alike, what do I know about powers? They're alike. So let's set up a mini equation. X equals -2. Now go solve. Done. Could I check my work? Sure, I could. Okay, I could take 2/3 and I could raise it to the -2nd power. By the way, your calculator can do that. Okay. And there's your head can do that as well. All right, number 5. Okay, so you remember how I said 95% of the time you're going to make your bases smaller, but there's one time when you're going to make your base larger. Okay, that one time that you make the base larger is when you're changing the 1. Okay, that's the one time I'm going to make a base larger. Now, right now, my 2 bases, I've got a 3 base and I have a 1. Now, I can't make my 3 base any smaller. There's nothing I can substitute into 3 to make it smaller. But I can make the 1 base into a 3 base. What does rule number 8 say? I don't remember. Rule number 6? Which one is that? What rule is that? 6? Okay. A to the what? 0. Equals. Oh, so I could change my 1 into a base of 3 if my base of 3 had a power of what? 0. Now, spoiler alert, we're going to get to the end of this and we're going to look at this and we're going to go, oh yeah, duh. Okay, so just be prepared. We're going to do that at the end of this. Okay, so let's leave the left side alone. 3 to the 5 minus x, and let's change the 1 into a 3 to the 0 power. Bases are alike. Let's set up a mini equation. So 5 minus x equals 0. So solve, and what do you get? I know I'm going to say 5 equals x, but it's the same thing. Now here's the duh moment, okay? Let's go plug that in. 3 to the 5 minus 5. Oh yeah, duh. Right? Makes sense. So, yeah, so, and that's not the only way to work that one, but it gives you practice with changing that 1 into a different base. All right, let's look at number 6. Okay, so number 6, we're introduced to a new number. It's called E. E is a number, you actually got an E on your calculator. And when you raise E to the first power, you get, it's like 2.71 something, okay? It's kind of like how pi is always 3.14159, etc. E is always 2.71, blah, 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 okay? And it's called the exponential base. I guess that's why somebody named it an E. I don't know, I'm guessing it was named an E long before English was around though. So anyway, my goal is still the same. E is just a number, okay? So my goal is still to get the bases all in. There's a little bit of work that I need to do though, okay? So on the right side, what rule can I use? Okay, what's it say?
That if you're multiplying the exponent, or like, if they're on, like one's on the inside, one's, the parentheses you multiply.
Okay, here's how I worded it. When you raise a power to a power, you multiply your powers. Is that what you're trying to say? Okay, when you raise a power to a power, you multiply your powers. Okay, so over on the right side, I'm raising a power to a power. What do I get when I multiply my powers? Negative 3x. So I've got e to the 3 minus x equals e to the negative 3x. Bases are alike. Logically, powers have to be alike. Let's set up a mini equation. So 3 minus x equals negative 3x. All right, what would you like to do? Okay, and what will you get? So x is negative 3/2. Now in this particular case, since I had x's on both sides, if I wanted to check my work, what I would do is in the calculator, I would use my E button, and I would say e to the 3 minus negative 3/2, and I would get an answer for that. And then I would go to the other side and type in another one, e, actually I would go up to the line above that, the original, and I would say e to the 3rd to the negative 3/2, yeah, right? And so I would type it in exactly the way that I see it, and I would look and see, did those two lines end up being the same? Okay, if I wanted to check my work on that. You're gonna get a massive decimal, but you could easily be able to see whether the two lines were the same. All right, so now I want you guys to work on number 7 together. Work on number 7. So not just, be quiet. You're walking yourselves through this. Abigail and Becca, you guys can discuss.
Yeah.
I thought it was 4 2, but 4 to the 4th, I think it's like 64.
Yeah. They're factors, but they're not. So you think it's 2?
Yeah, it's 2. What would be that 2 to the 5th? So the 2 to the 4th gives you 16. And then 2 to the 6th gives you 32. No, it'd be 2 to the 5th.
Yeah, 2 to the 5th. So 2 to the 5x equals 2 to the 4 minus 4x.
So we could do the base times the power to the power, so 2, 5x is equal to 2 to the 4th minus 4x. And you said equal.
What did you get? X equals 4.
So let's go plug it in and see if it works on both sides.
I want 2/3. X equals 2/3.
Now, Abigail, you know I'm gonna make you speak since you haven't been doing any speaking.
Yeah.
Is that an iPhone?
Yeah.
If you turn it on its side, it'll do exponents. It should be, I think, I don't remember if it's a caret or if it's an X to the Y. Mm-hmm. Clear for a minute. What are you trying to do?
I was just trying to.
Gotcha.
Did yours
So
work?
32 to the 4th. All right, so put in 32
10 for the 32.
and then plug that button,
and
that X
2
to Y,
and 5 for
and
the
then 4.
16 side.
and then
Did you try to simplify yours? Whoa!
Yeah, I simplified 1 to 2/3.
That wouldn't simplify. It wouldn't simplify. Because you're taking like the square root.
Yeah, I am.
So I got 4 of the 9. It worked.
Okay.
Making you work on this one, yeah? Okay, so Sarah got 2/3, Devin got 4/9. Abigail, what'd you get? Okay, Becca got 4.
Did you subtract 4x here?
I added it to the 5 that would give me 9x. So x equals 4/9.
Yeah.
Okay.
All right, Abigail. What'd you use for a base?
That's a good question. I'm confused on which one to use. Would be, because if you're turning, if you have to have the same basis, you turn it to a fraction, you use 2.
Yeah, so we would need to use a 2 base. What did you find happened with a 4 base when you tried a 4 base? Because 4 squared is 16, that works, right? But what's 4 cubed? 64 is too big, right? There's 4 to no nice power will give you a 32. So then we have to make our bases a little smaller, okay? So Abigail, if we're gonna use a base of 2, okay, let's look at the 16 first. When you have a base of 2, 2 to what power is 16? Go ahead, you can use your calculator, I don't care. 2 to the 4th. Okay, now that's where my 16 is, but don't forget, you still have a 1 minus x power that you haven't touched yet, okay? All right, now, Abigail, I'm gonna ask you, what about the 32? So 2 to the 4th is 16. 2 to what power is 32? 2 to the 5th. So let's take out the 32, but don't forget, you also still have that x power that hasn't been touched yet. Okay, so now what rule are we using? Yeah, raise a power to a power, we multiply our powers. So let's multiply the first pair of powers, and that's going to be 2 to the 5x. Okay, and on the other side we have 2. Now, Abigail, this is something that a lot of students make a mistake. So let's walk through it together. When you multiply these powers, what is it that you need to remember to do? Starts with a D. And it ends with distribute.
Yeah, distribute. For some reason I knew what we were doing, but I could not think of that word.
Yeah, exactly. So we're gonna distribute here. So then what is our power? When we multiply our powers, what do we get, Abigail? Good. Okay, so now our bases are alike. Let's set up a mini equation. Becca, is this where you went wrong? And the next step? Okay. Yeah, so we want to add 4x to both sides and then divide by 9. Does that make sense, Abigail? More sense? Okay. All right. Then I think we've got, so 9 is like super ugly. 8, not so much. I want you guys to work on number 8 together as well. And I'm going to give you a hint. It has something to do with our number 3 example. So you remember number 3, I said, don't think of this as 2/3 and 9/4. Think of this as 2s and 3s and 9s and 4s. This one is actually a little easier than number 3, because one side is nice, the other side is a fraction. Okay, but again, don't think of this as the fraction 1/2. Think of it as 1s and 2s.
So maybe we do 1 over.
We did it, 1/2 by -3. Maybe.
Yeah, that makes sense.
What if you just took the 8 and turned it into 2 cubed? And then we could do the
You could do 2
yeah,
-3 cubed.
and then that would give you the 1/2.
Yeah.
So we have to -1 times 3x minus 6 equals 2 to the 3rd.
So I got 1/2 to the -3x plus 3.
I'm still down on the 0x. x equals 3x.
Yes.
And does it work for both sides?
Yeah, fucking with it. You plug it into the original, right?
I would,
Okay.
because that, at least you know that is right.
Okay. It worked when I plugged it in. Are you plugging yours in?
Hers is a little more difficult.
Yeah. Androids have that app you can download and it has the
TI-80,
Yeah.
3 or 4.
Yeah, I think it's a 3.
Yeah.
Apple don't have it.
No, they don't. No, they don't. But Android also, well, we're not gonna go down that road.
Mhm.
Okay, so here's what I did or would have done, okay? I personally would have changed the 8 into a 2 cubed, okay? And I would have kept my power of x minus 1. And then in order to work with the other side and not have it a fraction, I would have changed the 2 and the 1, okay, to make that into a whole number. But when I do that, remember your power has to become negative or your power has to change signs. That's the whole power, not just a little piece of it. The whole power needs to change signs, okay? So if I change change signs on the power, that would have been a negative 3x plus 6. You with me? Okay, so now I need to clean up the right side. The right side would have been 2, raise the power to a power, multiply your powers. That's going to be 3x minus 3. This is 2 to the negative 3x plus 6. Bases are alike. So mini equation, negative 3x plus 6 is equal to 3x minus 3. All right, I'm going to personally take this guy to the right side. And so that would be a 3x plus a 3x, so that's a 6x. And then add 3 to both sides, that's going to be what, 9? Divide by 6, yeah, that's 9/6, but you're never going to leave 9/6 because that's an unreduced fraction. So Math 110 students, I don't have to tell you to reduce your fractions. So this is going to be, I'm running out of room here, x is equal to 3/2, which I think is what you said you got. Okay, does that make sense? All right, now let's look at the ugly one. Okay, so now go to rule number 8. Now go to rule number 8. Rule number 8 talks about changing any kind of a root into fraction powers. Okay, roots can be rewritten with fraction powers. Did I talk at all about trees and roots on the video? I don't usually do weird stuff on the video. I usually save that for class. So can you tell me exactly what does your rule say?
Root of a to the t power equals a to the power 2r.
This is the rth root. I gotcha. Okay, I misunderstood that at first. Okay. So notice that we have here the rth root. Okay. So this is the rth root. It's raised to the t power. For the record, that t power is allowed to be on the inside or the outside, and it doesn't matter. It does not matter. Okay. And this is the same thing as a raised to the t over the r power. Now, when you're outside, where are the roots on a tree? In the ground, at the bottom. So this is a way to remember this. Whatever your root is, whatever your root number, whether it's a square root, a cube root, a 9th root, or whatever, that's going to be your bottom number because roots are at the bottom of the tree. And whatever your power is, okay, think about a tree's power. The tree's power comes from the sun and the rain and the wind, etc., right? This is where the tree's power comes from. And so the tree itself, that's going to go up to the top. The power is on the top. Okay. Now, with that said, then, when I look at number 9, okay, so my base is whatever's on the inside. Okay, here's my base. This is my base. So my base is 5. If I'm changing my root into a power, how can I rewrite my fractional power? What's going to go on top? Negative x. And what number is going to go down on bottom? No, 3. Right? Because whatever the root number is, that goes on the bottom. Whatever the power number is, that goes on top. Okay, so then on the other side, how would you like to change the other side? Let's flip it. So let's make it into a 5/1. And then what is my power going to be? Negative x. Did you say minus or plus? Minus 2. Yeah. The whole power is becoming negative. All right. So now then my bases are alike. So I can make my powers into a mini equation. Negative x/3 is equal to negative x minus 2. Guys, an easy way to do this. This is not necessary, but it makes it easier because I know how much y'all love fractions and everything. Go back to chapter 5 in your mind. You remember how we solved rational equations? You remember how we got rid of fractions? Yeah, we multiplied by the common denominator, right? So when you look at this, what's the common denominator? 3, like the only denominator. So we multiplied by 3, and you can multiply by every single term. So what does the first term become when you multiply by 3? Negative x. Okay, somebody else, what does the next term become? And then someone else for the last term. And the cool thing is, guys, is that this original equation, this mini equation, this is the exact same equation as this one. Question is which one do you want to work with? You know, do you want to work with the one with fractions, or would you rather work with the one with whole numbers? And it's your choice. If you want to use the fractions, I'm fine with that. Okay, so I say let's add 3x to both sides. So what's x? And once again, you could plug that into the original. I'm not going to take the time to do that, but you could plug that in. Actually, the left side, look at how easy the left side is. If you plug in a -3, this is going to become a -3. Well, what's a cube root and a cube do to each other? They undo each other, just leaving you with a 5. If you plug in a -3 here, you have 2 minus 3, or -1. With that -1 power just makes you flip it, right? So now I've got a 5. So that one was an easy one to plug in. Okay. All right. I love getting to talk about this section because it's money. Like, who doesn't want to talk about money, right? It's the one section that makes sense in this course, right? I mean, like, all this apartment's going to exponents. Well, really, we're doing exponents so that we can do stuff like this with the money. And so this is a time where I always want to just take a minute and be a real human being with you instead of just a math geek teacher. And I want to share with you just some opinions that I have. You can totally disagree with my opinions, and that's fine. And it won't even affect your grade if you disagree with me. Every other time in this class, when you disagree with me, it affects your grade. So when it comes to money, one of the things that I really want to point out to you in this section, and then a little bit further down the road in the same chapter, is how you can make money work for you, or you can always be working for your money. Who's going to be the master? Who's going to be the slave? And so that's one of the things that I really want to point out through the next few questions even. But a short story, back when I was first teaching, I was teaching in a small private school. I was getting paid next to nothing. I remember I had accumulated some debt. It wasn't much, it was maybe $3,000. Okay, by the way, the national average is quite larger than $3,000. So I had accumulated some debt, and but because I made so little, that $3,000 felt massive. And I had a car payment. I had purchased some furniture for a house. I had purchased a house. And I'm not calling my house debt because to me a house is an investment. So I'm not even including that in my debt. But I had purchased some furniture for my house because I was moving into a house. I needed some furniture. And there was a couple other things, little things, you know, that I had just simply needed. And so I was under this blanket of debt, and you know how sometimes when, and I know as college students you understand this, you feel like you're so poor that you can't even go to the thrift store. Like, you know, which is one of my all-time favorite things to do. And I would be on the phone with my mom, like, I feel like I can't even stop by the thrift store because I don't have the money to stop by the thrift store. And or on a different note, you know, I had a student who was going on a mission trip and they were raising funds for a mission trip, and I would feel like I couldn't even contribute to this mission trip for my student because I just didn't even have enough for my own self. So I remember I had this surprise. Somebody actually sent me a $5,000 check in the mail. This person I hardly even knew. I think I'd only ever had a conversation once with them. And there was no reason for her to have done that, but at Christmas one year she sent me a check for $5,000. And so I paid off all of my debt. And from that point on, I was like, I'm not going back into debt. I'm just not doing it. Now, some people are like, well, do you have a credit card? I do. Okay. I have a credit card. But for many years, I did not. I would not allow myself to have one. I did get a credit card so that I could earn points for travel because I go to Poland 2 out of every 3 summers. So I like to earn my points that way. But I pay my credit card off every month. It never, ever, ever has a debt on it. So I kind of swung from one end of the spectrum to the other. So I got myself some savings accounts. And the first thing I established was an emergency fund. Like from now on, I'm going to keep a certain amount of money in that emergency fund. I typically, 3 to 6 months is what of wages I like to keep in there just in case something happens. I think we've talked about how much dogs cost. Miles, close your ears. Dogs are expensive, and so my dogs have their own savings account. They get $100 a month, and that money goes into their savings account, and when I have to go to the vet, the money's there. I don't feel like I'm hurting. I mean, I don't like to fork out $300, but at least the money is there, and I don't feel that frustration of pulling out of nowhere or going into debt to go to the vet. My car has its own savings account. My house has its own savings account. And I have gone a little crazy with all of this, but nonetheless, this is my way of not going back into debt. And I'll be transparent with you. I just told you, I purchased a vehicle, and my other vehicle had just turned 11 years old. Was still running well, but I live in Taylor, so I have quite a distance to come. I was afraid that I was going to get to the point where I wasn't going to be able to sell it for what I wanted to sell it. During those 11 years, I was able to pay cash for that car. During those 11 years, I was still making car payments to myself. And so I had saved to the point where I was almost ready to get another car. So I did purchase my car in April, and she said, well, did you go into debt for it? I did. It was a very, I don't mind sharing numbers with you. I think that it ended up, I was able to put $16,000 down on the car, which left $3,000, I think, to pay. So I have, my car payment is $100 a month. It isn't, and I'm paying over $200 a month because I want to get this paid down in a year to a year and a half. Because as soon as I do that, I'm still making car payments to myself for the next car. I'm hoping this car will last 10 to 15 years. And with it being electric, it's supposed to last longer than your typical car. And so I'm hoping that within the next 10 to 15 cars, I will have saved for the next vehicle. And so that is my plan, so that I don't have to go into that. So I did go into debt for my car. I do own a house, so, but again, I call that an investment. But other than that, I have no debt. I say all that because I want to show you by the numbers what debt can do, okay? And I would challenge you, you guys are all young, all right? I could be your moms, all right? Yeah. So I challenge you that from a young time, start saving. If you want something, save for it. Don't go into debt for it, save for it. Be patient. It will help you to stay away from impulsive purchases. I'm bad about impulsive purchases. Amazon is, we have a love-hate relationship. Because I hate loving it so much. Because I get myself in trouble sometimes. And I get to the end of the month and I see what I spent on Amazon. I'm like, man, I gotta pay all of that off. What was I thinking? But from a young age, learn to set up an emergency fund. Learn to set up a savings account. Be saving for your next vehicle. Be saving for a home. I'll tell you right now, my credit score, there was a window of time where I had sold my house in Charleston. I still had not purchased my house up here in Greenville. And so my parents have an apartment on their property and I was living in there, and my credit score plummeted. You know why? Because I had no debt. Now, I'm okay with a horrible credit score if I have no debt, okay? And so I went to purchase my next home, and I had a decent amount to put down on the home. And, some people are like, you're never gonna be able to buy a house because your credit score is so bad. I'm like, you're right, unless you can get somebody to not just plug in numbers into a system. If you can get a person to look at, I've got 20% to put down, I've got 25% to put down. They don't care what your credit score is at that point. No. If you have enough cash, if you walk in with cash to pay for a car, they're not gonna tell you, sorry, you can't do that, your credit score is bad. No. They're gonna take the cash. Cash loans. Exactly. So my point is at a young age, don't go down the road that's normal. Be weird, okay? Don't get into debt if you can help it. If you cannot help it, pay it off as fast as you can. Do whatever, sell everything you can find in your house, so that the kids and the dogs are hiding because they think they're gonna be sold next, all right? I mean, get rid of the debt as soon as you can. All right, so that's my little blurb that I love to. So let's talk about the numbers and let's look at what I'm talking about here. So the first thing is that you had to fill in some extras. Quarterly, what is your end value going to be? 4. And then monthly? And daily? 365. Now this one, I'm just going to give a little bit of a disclaimer. Some textbooks will say that daily is 360. This one doesn't. It says 365. And the reason for that is they're allowing for 5 holidays in the year, 5 major holidays in the year where interest wouldn't be taken. So I've seen varying things on that daily, but for our textbook, we use 365, which makes sense. Again, I try not to be weird on videos because people who are not my students sometimes watch my YouTube videos. But what I like to do is I like to call this guy the shampoo formula. You're too young to get it. You've never heard of Pert shampoo, have you? Okay. Yeah, only people who are over the age of 60 know what that is. Okay, so Pert shampoo, they still sell it. One semester, I had a student walk in and say, Ms. Roberts, you are never going to believe what happened to me. What? I went to visit my grandparents this weekend, And do you know what was in their shower? Pert shampoo. Look, I thought you were making it up. Okay, so it really is a thing, Pert shampoo. So I call that one the clean formula. Okay, because shampoo cleans. I call this one the clean formula. I call this one the dirty formula. It's uglier anyway. Okay, clean formula versus dirty formula. All right, so let's take number 10. And let's take $15,800, which I think is a fairly normal price for a vehicle ish. For somebody who's probably well established in a career.
Yeah, I do buy new figures. I don't like new things.
Oh, I don't buy anything new. No. You drive it off the lot and it's like immediately decreases in value. No. I buy used. I've never had a new car. New to me, but not new. So $15,800, I think is a normal average price for, you know, Honda Accord or whatever, just a normal car. Do you guys know what a normal interest rate would be for a car? Okay, so that is actually, so let's go with the annual interest for 36 months would be how many years? 3 years. And actually, they gave me mine over, I think it was 6 years. Like, I am so not taking 6 years to do that. It'll be 1 or 2 years.
They did mine for 4.
Mm-hmm. But do you know what the normal interest rate would be? Okay, so let's just do 4% to make our lives easier. I must have gotten a really good deal because my interest rate was 2% and they gave it to me for 6 years. So I think that's why I was able to have $100 car payment. All right, so then let's figure out what are we actually going to pay for this car in 3 years' time? Okay. So let's find out if the interest is compounded quarterly, which formula are we going to use? The dirty formula or the clean formula? The dirty formula, okay? So we've got here A equals P times the quantity 1 plus R over N, all raised to the NT power. Bless you, bless you. Okay, what's the principal amount? Okay, the money, what I'm starting with, it's my initial amount or my starting amount. So this is $15,800. We've got 1 plus. What's my rate and how will I write it? It's 4%. How will I write it? 0.04. By the way, if we had used the 4.5% that Devin said, this would have been 0.045. Okay. Over N, what's my N for this question? It would be 4. Why is it 4? Because it says quarterly. So quarterly is 4 times per year, and N is the number of times per year. And we're going to raise this to the NT power. So what's N again? 4. And T is 3. And by the way, time is always in years. So what if it were, what would I use for T if I said you're going to have this loan for 6 months? Half of a year, so that my T value would be a half. Okay. So it's all, you wouldn't put a 6 in for 6 months. You would have it in years, which is half a year. All right. So what you want to do is take out your calculator. Becca, you want to use mine? I think you're going to want it. All right, and you're going to type in exactly what you see. So type in 15,800. Now, don't get ahead of me because I am going to give you a tip here. Open up a parentheses, 1 plus. You don't need a new set of parentheses, 0.04 divide 4. It won't hurt if you have them, you just don't need them. Close your parentheses, use your caret. Here's the tip. Now, if you just type in 12, you don't need to listen to what I'm gonna say, but sometimes you're gonna have something that's, like, what if that had been that, well, never mind. What if it had been daily, and so we had 365 times 3? Well, you can't do that one in your head so much, right? So the tip here is that after the caret, use a set of parentheses around the whole power, and don't use parentheses in between, use the times sign in between. And then push enter. Now I have no idea what the answer is going to be because we chose a new set of numbers. So help me out here. What does the car cost me by the time 3 years is up? 803. And what's the decimal? 835. Okay, yeah, 84 cents. How much extra did you pay just to get a car loan?
200.
$200. $200?
And $3.84.
$2,000.
Oh.
What could you do with $2,000?
You could buy you another car.
Buy another little car.
You could buy a 4-wheeler.
I mean, $2,000. I mean, this makes me want to, up my car payment to $300 instead of just $100 or $200 a month. And get rid of that debt, right? Because $2,000, that's just, and this is a pretty good, normal car loan, right? Okay, so let's flip that. What if I invested $15,000? What if I came into an inheritance or, something, I don't know. And I invested $15,000 and just left it alone for 3 years. Gained $2,000 with no work involved. That's kind of nice. So this is when I go back to, are you going to be slave to the money? Are you going to make the money be the slave to you? Who's the master here? Right? And this is something that you want to decide from early on. Now let's try it also compounding continuously. Continuously simply means continuously, like it's not just every quarter or every month or every day. It's every single second of every single moment of every single minute of every single hour of every single day, right? Continuous. And it's an infinite number of times. And it's not like I can type in to my calculator over here in my formula. I can't type in an infinity for n, the number of times per year. Okay, so this is continuous, so I need a new formula for this. So this is my clean formula. So we've got principal times my magic number e that we talked about a little while ago, raised to the RT power. So once again, your principal is 15,800 times e. What was our rate again? 0.04 times, what was our time? 3. Now, do you see where the E button is? Should be over on the left side. Do you see an LN button? It's right up above the LN button. Do you see it, Abigail? See it? How did you find it? Okay, so again, you can type it in exactly the way you see it. The only thing, the tip I would give is put one set of parentheses around the whole entire power. Okay, so 15,800, use your E button, 0.04 times 3. And what do you get this time? 44 cents? 45 cents. Now, what's the difference between compounding continuously and compounding quarterly? $11-ish. You get more compounding continuously simply because they're taking that interest all the time. They're never stopping. Okay. Any questions on that?